Hello there, we are back with the ordinary level physics, and this time we are looking at one of the 7 topics or branches of physics, and this is the topic of waves. Now I request you to kindly have the following with you. Please have a book for taking notes, don't just watch this video, record something down, a pen for writing, a calculator because we shall have many calculations. And please be open-minded because you have to be ready to learn very many things that shall be handled here. I am a teacher at Seroma Christian High School. It's located in Mukono, Uganda, East Africa. And my name is Dennis Monday. So my YouTube channel is named after my name. It's Dennis Monday Uganda. It has very many resources that can help you better your performance and your understanding of the physics subject. I kindly advise you not to watch this video online, but to download it in the best resolution available. And yes, you can actually use any downloader like TubeMate and other downloaders that can help you get this video. If you have it offline, if you have downloaded it, you can pause it, you can listen, you can watch over and over again until you comprehend the areas that shall have been handled. Okay, let's dive into the introduction. By definition, a wave is a periodic disturbance in a medium which transfers energy from one point to another without causing permanent displacement of the particles of the medium. We are saying a wave is a periodic disturbance in a medium which transfers energy from one point to another without causing permanent displacement of the particles of the medium. Now there is a term which is similar to a wave. For it, it's not periodic. Or it's not repetitive. It happens only once, and that's what we call a pulse. So if you're defining a pulse, you say a pulse is a single disturbance. Just look at this. Where there was the word periodic, we're just replacing with single, and the rest of the words remain. So a pulse is a single disturbance in a medium which transfers energy from one point to another without causing permanent displacement of the particles of the medium. I want to draw your attention to this point here. I said a wave is a periodic disturbance in a medium which does something. It transfers energy from one point to another without causing permanent displacement of the particles of the medium. So a wave actually transfers energy, but it does not cause permanent displacement of the particles of the medium, meaning that the particles of the medium will have to remain after the wave has passed. They will remain in their original positions actually, if there are many. Yeah. Okay, now let's look at categories of waves or types of waves. Like human beings, waves can also be categorized in comparative pairs. Human beings can be categorized as male or female. That's comparative. You can I can say comparative pairs because you can have human beings grouped in that way. You can have male or female. You can have young or old. You can have rich or poor. You can have human beings who are beautiful or ugly. Yeah, just comparative categories. Now even waves can be categorized as transverse or longitudinal. So we have transverse waves and longitudinal waves. If you don't categorize them that way, you can categorize them as mechanical or electromagnetic. And also you can categorize waves as progressive or stationary. Now we categorize waves as transverse or longitudinal depending on the direction of vibration of the particles of the medium relative to the direction of the wave. And then we categorize them as mechanical or electromagnetic depending on how they are produced, because mechanical waves are actually produced by mechanical vibration. Electromagnetic, as you see, electro and magnetic. These will result from combinations of two fields which will be perpendicular, an electric field and a magnetic field. And then stationary stationary and progressive waves. These are categorized depending on whether there is superposition or no superposition. A progressive wave is one actually that moves from its source and spreads out continuously, but a stationary wave will not carry energy from one point to another. So there will be actually two progressive waves, one carrying energy from one point to another, and then the other one carrying energy in the opposite direction. We shall look at the details of each of these waves, these types of waves in the later areas. Okay, for now I want us to now understand what transverse and longitudinal waves are. This topic is just aimed at introducing transverse and longitudinal waves, and we shall go even into calculations of waves that are of this type. Now, you need to know two phrases if you want to define longitudinal waves and transverse waves. Just look at this. Direction of vibration of the particles of the medium. This is the first phrase that you must understand. We are saying the direction of vibration of the particles of the medium, and the second phrase is the direction of the wave. So we are looking at two directions which are going to help us define transverse and longitudinal waves. The first one is the direction of vibration of the particles of the medium. So the direction of vibration of the particles of medium here. And the second phrase is the direction of the wave. So if you are defining a transverse wave, you will say a transverse wave is a wave in which, and then you put the first phrase, the direction of vibration of the particles of the medium is perpendicular. So the direction of vibration of the particles of the medium is going to be perpendicular to the direction of the wave for the transverse waves. Do you understand that? So I'm saying a transverse wave is a wave in which the direction of vibration of the particles of the medium is perpendicular to the direction of the wave. Now, what about if you're defining a longitudinal wave? For it, you will still use the same phrases, but instead of saying perpendicular, just put the opposite, which is parallel. So we will say a longitudinal wave is a wave in which, now we put phrase 1, the direction of vibration of the particles of the medium is parallel to the direction of the wave. So just understand this scheme and life is going to be very easy for you. Now let's define these two definitions. Let's define the two types of waves. The first one, a transverse wave is a wave in which the direction of vibration of the particles of the medium is perpendicular to the direction of the wave. You see? We're just picking it from here. We are saying a transverse wave is a wave in which the direction of vibration of the particles of the medium is perpendicular to the direction of the wave. And this is the definition we've written here. A transverse wave is a wave in which the direction of vibration of the particles of the medium is perpendicular to the direction of the wave. What about a longitudinal wave? A longitudinal wave, for it, when we're defining a longitudinal wave, we just only replace where there was perpendicular for transverse wave. For a longitudinal wave, we put parallel. So a longitudinal wave is a wave in which the direction of vibration of the particles of the medium is parallel to the direction of the wave. I think these definitions are very easy for anyone to put in their brain. They just sound like someone rapping. A longitudinal wave is a wave in which the direction of vibration of the particles of the medium is parallel to the direction of the wave. You see? Very, very easy for you. Okay, we're going to make some demonstrations of transverse and longitudinal waves using a slinky spring. And there is a simple animation here. Please watch it.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
Now, examples of transverse waves include water waves, earthquakes. The water waves, like you've experienced them at the beaches. Yeah. Waves on plucked strings, radio waves, TV waves, lights, X-rays, we have gamma rays, we have infrared. Actually, I just said plus all other electromagnetic waves. Now, all electromagnetic waves are transverse. Electromagnetic waves are many. We have radio waves, TV waves, light. We have ultraviolet. We have ultraviolet radiations or ultraviolet waves. We have infrared. Infrared is used for, like if you're using a remote to control the TV, you're using infrared radiations or waves. We have gamma rays. We have X-rays. Yes, we have radar waves. So many electromagnetic waves, and all of them are transverse. Examples of longitudinal waves include sound. The one that I am using to speak to you is a longitudinal wave. Sound is a longitudinal wave. Waves produced on sling springs. Now, sling springs can be used to produce both longitudinal and transverse waves, as you've already watched in the video. And then waves produced in pipes. Yeah. Okay, now let's look at a transverse wave profile. A transverse wave profile, like how does a transverse wave look like? We shall have two axes, the vertical axis and the horizontal axis. The vertical axis represents the displacement of the particles of the medium from their equilibrium position, and the horizontal represents the distance traveled by the wave. So I've put displacement of the particles, y in meters, and then distance traveled by the wave, x in meters. Now, this is a transverse wave profile. A transverse wave travels in that kind of style. Now, this portion here, or this position here, where a particle has maximum displacement from the equilibrium position. The equilibrium position I've represented with this horizontal line here in pink. This part here is called a crest, and then down here is called a trough. We are going to look at the definition of each of these, a crest and a trough. Now, from one crest to another, the distance between them is called wavelength, and is denoted by the Greek letter lambda. It's like an inverted Y, lambda. Also, from one trough to another, still it's the same distance, which we call lambda, wavelength lambda. And on the other hand, for one cycle, you see that's one cycle, one complete cycle. This is a half a cycle and another half. So a complete cycle is there, like you've seen in that animation. And the distance traveled by one complete cycle still gives the wavelength of the wave. And you also have to know that if you take two particles that are in phase, there is a particle here and another particle here. We shall understand what it means for particles to be in phase. A particle here and a particle here. Actually, these two particles will be doing the same thing. They have the same velocity, they are moving in the same direction. In simple terms, they are in the same step of vibration during the wave motion. So still the distance between them will be the wavelength, which we denote by lambda, a Greek letter, lambda. Now, we have two types of transverse wave profiles, and the difference between them is just the horizontal axis, which may represent distance, or for the second one, it represents the time traveled by the wave. For this time, still we shall have the vertical axis with the displacement of the particles from the equilibrium position, and the horizontal. But this time, the horizontal axis will have the time in seconds. And here we are still having our transverse wave profile. The time taken for a wave to make one complete cycle, this time here is called the period of the wave. It's called the period, and the period period is denoted by capital letter T, period T. And still the time interval between two crests from one crest to another, that time interval is still a period. So please understand these two profiles. This first profile here, the first profile had on the horizontal axis, we had distance. We had distance, but for the second one on the horizontal axis, we are having time in seconds. Okay. Now let's look at these definitions. A crest is a position of maximum positive displacement on a transverse wave. So we are saying a crest, if they ask you to define a crest, what is a crest? What do you say? A crest is a position of maximum positive displacement. You see, this is going upwards. Maximum positive displacement of a particle. You can just say of a particle, by the it's a particle of the medium from the equilibrium position. You can just say a crest is a position of maximum positive displacement from the equilibrium position. And a trough where there is positive, you will put negative, because you see for it is going downwards. The displacement is downwards. So we will say we are going to define a trough as a position of maximum negative displacement on a transverse wave. A trough is a position of maximum negative displacement on a transverse wave. Now let's look at a longitudinal wave profile. I want to start with a simple animation. Watch this. So from there, you realize that we are having basically two regions of a transverse wave. We have the region where the particles are close to each other, and that is called a compression. And we have a region where the particles are spaced, that is called a rarefaction. Just one word, don't separate the two words and write rare and then faction. It's rarefaction, one word. Now, the distance between two successive rarefactions gives us still the wavelength, lambda. And also the distance between two successive compressions. You see, I'm taking the middle of the compression and the middle of a compression here. Still gives us the wavelength, lambda. Now, you've observed that a longitudinal wave from the previous diagram here. A longitudinal wave has two regions. We have a compression and a rarefaction. Compression, rarefaction. Compression, rarefaction. Just like that. So a longitudinal wave has two main regions. One is called a compression and the second one is called a rarefaction. So our longitudinal wave has compressions and rarefactions. Now a compression is a region in a longitudinal wave where the vibrating particles are close to each other, and a rarefaction is a region in a longitudinal wave where the vibrating particles are spaced. Please don't forget these two definitions. Put them in your mind. You can pause and write them down. Now, terms used in wave motion. The first one is what we call the rest position. Rest position. I want now to explain and to define each of these terms. We've just mentioned a little about them. Rest position. What's the rest position or the equilibrium position? This is a position of zero displacement of a particle on a wave. You remember? Like here, for a transverse wave, the rest position for a longitudinal wave will be that position, for example, here, where the particles will neither be close to each other nor spaced, but they remain the way they were. So around maybe this region here. This here will be like the rest position. For a transverse wave, yes, we just represented it with a horizontal line here. Okay, now we are defining, come on. Yes, we said a rest position is a position of zero displacement of a particle on a wave. A cycle or an oscillation is a to and fro motion of a particle in a medium. A to and fro motion of a particle in a medium. So like if a particle is here, it moves this side, then it goes this way and comes back. That's what we call one cycle or one oscillation. Amplitude. Amplitude is the maximum displacement of a particle from its equilibrium position, or you can say it's the maximum displacement of a particle from its resting position. That's what we call amplitude. Period. Period is the time taken for a particle to make one complete oscillation, or you can say it's the time taken for a wave to make one cycle or one complete cycle. Now, in most cases, when we talk about cycles, we can refer to both particles and waves. But when you're talking about oscillations, in most cases, for oscillations, we limit them to the particles only. So the SI unit of period is the second. And by the way, the SI unit of amplitude is the meter. Don't forget that. Frequency, you learned this in primary. Frequency is the number of complete oscillations made in 1 second. Or you can say the number of complete cycles a wave makes in 1 second. That's what we call the frequency, denoted by letter F. And the SI unit of frequency is the Hertz. Hertz is H, then you add T and the Z. So you end up with Hertz or Hertz, but it is Hertz. It's named after a very great physicist who did a lot of research about waves. He was called Heinrich Hertz. So the SI unit of frequency is the Hertz, after Heinrich Hertz. By definition, a Hertz is defined as the frequency of a wave which makes one complete cycle in 1 second. Now, if a wave makes one complete cycle, if it takes 1 second to make one cycle, then the frequency of that wave is what we call a Hertz. A Hertz is the frequency of a wave which makes one complete cycle in 1 second. Please don't forget that definition. Other common units of frequency include, instead of using just Hertz, we have kilohertz, megahertz, gigahertz. You can have terahertz, you can have many hertzes, or I should say many other units. Now, when we say a kilohertz, oh my god, this was supposed to be a small k. We are saying 1 kilohertz. 1 kilohertz. Please, it's not supposed to be a capital K. Don't make it a capital K. It's supposed to be a small k. So you write 1, then kilo, like this. Yes, this one was okay. This is the correct one. 1 kilohertz. Don't write it like and make it a capital K. 1 kilohertz is equal to 1000 hertz. You know, K means 1000. Or kilo means 1000. 1 megahertz, that's 1 million hertz. 1 gigahertz, 1 billion hertz. Yes, don't forget that, please. Now, let's look at the equation which relates frequency and the period. Frequency, which is small f, and period, capital T, are related by the equation f is equal to 1 over t, and on the other hand, t is equal to 1 over f. Now, how do we derive that? Consider a wave which makes n cycles in t seconds. It is making n cycles in t seconds. So its frequency will then be, remember, frequency is the number of complete cycles made in 1 second. So you'll have number of cycles divided by the time. You get number of cycles made per second. That's a frequency. On the other hand, the period is the time taken to make one cycle. So it's time taken over number of cycles made. So you see, f is equal to n over t, t is equal to small t over n. So equation 1 and equation 2, if you multiply them, f and t, if you multiply f times t, you get ft. n over t times t over n I've illustrated here, and we are ending up with ft is equal to 1. We are getting 1 because n will cancel with n, t will cancel with t, and therefore we say thus f is equal to 1 over t. If you divide through by f you're going to end up with f is equal to 1t. Or if you divide through by if you divide through by t, you'll end up with f is equal to 1 over t. And if you divide through by here by f, you end up with t is equal to 1 over f. Both equations are very important for you to remember. Please don't forget them. Now, the sixth term, one of the terms used when we are describing wave motion, is what we call wavelength. And wavelength has so many definitions. The first one, wavelength is a distance between two successive crests. The second one, wavelength is a distance between two successive troughs. The third one, wavelength is a distance between two successive rarefactions. The fourth one, wavelength is a distance between two successive compressions. The fifth one, wavelength is a distance between two successive particles which are in the same phase. Oh, my battery is running. Wavelength is the distance between two successive particles which are in the same phase. And the sixth one, we say wavelength is a distance traveled by one cycle of a wave, or covered by one cycle of a wave. Now I want you to note this. The first definition and the second one apply only to transverse waves. The third and the fourth, they apply only to longitudinal waves. And then the last two, that's definition number 5 and number 6, they are general definitions. So if they ask you to define wavelength as applied to transverse waves, you use any of the first two. You can say wavelength is a distance between two successive crests. Or you can say wavelength is a distance between two successive troughs. Please don't say successful, but successive. And then if you look at definition number 3 and number 4, because we have rarefactions and compressions, these apply to longitudinal waves. So if they say define wavelength as applied to longitudinal waves, don't use the first definition, they will cross you. You say wavelength is a distance between two successive rarefactions, because they have asked you to define as applied to longitudinal waves. Okay, I'll not talk about the rest. Now the SI unit of wavelength is supposed to be one word. Please mark this. It's one word. Sorry, I made a mistake here. The SI unit of wavelength is the meter. Now phase, this is the seventh term that we use in wave motion. Particles are said to be in phase if they are in the same step of vibration with one another. That means they have the same amplitude, they have the same speed, they are moving in the same direction. Those particles are said to be in phase. So particles which are in antiphase are those which are in opposite steps of vibration with one another. Number 8, or term 8, is what we call wavefront. A wavefront is a line or curve joining particles which are in phase in an advancing wave. I will show you an animation to illustrate what we mean by a wavefront. So let's first look at this array. Array is a line perpendicular to a wavefront with an arrow which shows the direction of the wave. Array is a line perpendicular to a wavefront with an arrow which shows the direction of the wave.
We can do an experiment to look at what happens when we generate a wave by dropping a stone in a pond. As the stone hits the water and sinks, it creates a set of circular waves that radiate out from the point of impact. The waves can move objects in the water or at its edge. To do this, they need to possess energy. So where does this energy come from? Well, some of the kinetic energy the rock has as it hits the pond is converted into energy that is carried away by the waves. So waves carry energy. Do waves also carry water along with them? To see, let's zoom in on the actual surface and pick out some points to observe. If you look carefully, you'll see that the water actually only moves up and down. It does not travel along with the wave. Waves carry energy without carrying matter.
And the last one is what we call the velocity of a wave, or you can call it the speed of a wave. We denote it by letter V. Wave velocity or velocity of a wave is just the distance moved by the wave in 1 second. Distance moved by the wave in its direction in 1 second. You can just say the distance moved by the wave in 1 second. So the SI unit of wave velocity is meters per second. Remember from primary you learned that speed is equal to distance over time. We are going to use this formula to make the derivation of what we call the wave equation. This formula here, speed is equal to distance over time. So let's look at the wave equation. The wave equation is denoted by V is equal to lambda F. V stands for or represents the velocity or the speed of the wave. Lambda is the wavelength and F is the frequency of the wave. Please don't forget this equation here. How does it come about? Let's derive it. Now, for one cycle of a wave, the distance covered is the wavelength, or is just one wavelength, and the time taken to cover that one wavelength is the period of the wave. So from speed is equal distance over time, realize that the wave speed V is going to be wavelength, because the distance is going to be wavelength for one cycle, over period, which is going to be lambda over t, because wavelength is lambda and period is t, which we can go ahead and write as lambda times 1 over t. Lambda times 1 over t. These two equations are the same, which actually becomes lambda f, because 1 over t is equal to f. You remember we talked about that. 1 over t is equal to f. Therefore, you see this shows that V is equal to lambda f. Therefore, V is equal to lambda f. Now note, the speed of any electromagnetic wave in a vacuum, or the velocity of any electromagnetic wave in a vacuum. The electromagnetic waves, I hope you remember them. The X-rays, the gamma rays, the ultraviolet, the infrared, the microwaves, the TV waves, radio waves, all of those are called electromagnetic waves. So in a vacuum or even air, their speed is 3 exponent 8 meters per second. That is 300 million meters per second. Now note number 2. If L is the distance between any successive crests or troughs or compressions or rarefactions made in t seconds or in time t, then the wavelength and period can be obtained using the equations n minus 1 into lambda is equal to L, and n minus 1 into t is equal to t, where this is n minus 1 into capital T is equal to small t. Remember, n minus 1, this will be representing the number of cycles. N minus 1 times the wavelength should give you the total length between the n cycles, and n minus 1 times the period should give you the total time taken to make those n cycles. Just think about this. It's very basic. You can actually put these two equations in your mind. Examples. We are going to look at examples concerning waves, but before we look at the examples, let me show you a few animations here. Actually, maybe let me show you one, and I'm going to ask you to tell me some things about this animation. Okay, now I want you to look at this particle here and how it's moving, and you will tell me in which direction this particle will be moving. If the direction of the wave is that one shown, in which direction does it move? Is it moving to the left or to the right? Let's play it one more time, and then you still tell me in which direction it moves. One more time. You see here, when you draw a line, I've put here a vertical line, and then we're going to play this one more time. When you put a vertical line here, you realize that this particle is just moving downwards and upwards. Okay, now let's look at examples. Example number 1. The figure below shows a transverse wave profile. So we have a vertical axis representing the displacement in centimeters, the horizontal representing the distance in meters, and there we have a transverse wave profile. There is a part labeled A, a part labeled B, and then they told you that the distance between this part and this part there, the vertical distance is 10 centimeters. So questions: part A, name the parts labeled A and B. What did we say part A is? Part A is a crest and part B is a trough. If you name them that way, thank you so very much. Part B says calculate the amplitude of the wave. Remember, we said amplitude is the maximum displacement of a particle from its rest position. Now you see, they gave us the distance from this peak again, and they went down to the bottom peak, upper peak and the bottom peak. So you realize that the amplitude is just half of that length given. Therefore, amplitude is going to be the 10 centimeters divided by 5, which will give us by 2, which will give us the 5 centimeters. Example number 2. The distance between 6 successive crests of a wave is 20 centimeters. Determine the wavelength of the wave. Now remember, these are just a few crests. We have, let's represent some here. How many crests are represented here? I think we have around 7. But then, the distance between 6 successive crests of a wave, we have been told is 20 centimeters. Now ask yourself, how many wavelengths here are represented? For transverse wave, wavelength is a distance between 2 successive crests. So from one crest to another is 1 wavelength, another wavelength, another wavelength. Those are 3, 4 now, then 5, you see? So it means that this distance here, when you add 5 plus 5 plus 5, when you add lambda plus lambda plus lambda plus lambda plus lambda, you're going to end up with 5 lambda. 5 lambda, which will equate it to the 20 centimeters, and therefore in the calculation here, you're going to end up with lambda is equal to 4 centimeters, which can be written in the SI units as 0.04 meters. Now, alternatively, if you didn't use that, you can use the formula we just wrote. We said n minus 1 into lambda is equal to L. L is the total distance from here up to here, and then small n is the number of crests or troughs, but here they gave us crests. So because they are 6, so we say 6 minus 1 into lambda is 20, and similarly in the same way we're going to end up with lambda is equal to 4 centimeters, which is equal to 0.04 meters. I always encourage you, please, you pause these videos and watch. Okay. Example number 3. A wave makes 251 crests in 40 seconds. The distance between the 251 crests is 10 meters. But they are saying determine part A, the period. Part B, the wavelength of the wave. Now, honestly speaking, do we need to do this? Okay, we can. Let's do it together. Let's do this together. We do this together. We do this together. Now, for example number 2, they gave us only 6 crests. They told us the distance between 6 crests. Here there are 251 crests, my friend. There is no way you're going to draw them on your small paper. You won't. So let's just straight away use the formula. You know the formula. So in our solution, we are going to say, because they are asking for the period, so we'll use n minus 1 into the period is equal to, what was the total time? 40 seconds. The n, there were 251 minus 1 times t is equal to 40 seconds. So t is equal to 40 over 250, and you get here an answer. You write it in seconds properly. My stylus is I have no stylus and this thing is disturbing. Now Roman 2 says wavelength. So for wavelength, you still use the formula for wavelength. N minus 1 into lambda is equal to capital L here. So what was n? You put 251 minus 1 into lambda is equal to the total length. They told us 10 meters. Yeah. So lambda is going to be 10 over 250. And then you get an answer here in meters. Number 4, the figure below shows a sound wave produced from a tuning fork vibrating at 800 Hz. This is the diagram. Part A says calculate the velocity of the wave in the medium. Calculate the velocity of the wave in the medium. Now look at this. They gave you the distance between one crest, between the compression and the rarefaction, the middle positions of a compression and that of a rarefaction. That means the wavelength here, if this distance is 20, then the wavelength is twice of that distance, which is going to give you 40 centimeters. Convert that to meters and use it in the wave velocity. Now here we are going to write and say, remember velocity v is equal to lambda, lambda is jamming, lambda f, which becomes, what is the lambda? The lambda is 0.4 times 800, which will give us, going to give us 300 and, my god, this thing is disturbing. So here we're getting 320 meters per second. Determine the period of the wave. You all know how to get period. The period is equal to 1 over f. The f is 800, so just say 1 over 800 and you get me the answer. Now number 5 is like that. The figure below represents a wave. There we are. It represents a wave. Mark on the diagram the amplitude and label it A. This question was a unique question which was set in 2012, paper 1 number 44. They said mark on the diagram the amplitude and label it A. Part B, how many cycles are shown on the diagram? And part C, calculate the period for the wave or of the wave. Now do you see, that is what we call the amplitude. Now you're going to do me a favor and answer part B and part C, please. Number 6, the figure below represents a wave motion in which a crest moves from O to P in 80 seconds. Question is there. Find the amplitude, the wavelength, and the frequency. This is also your question. Number 7, 2010. Number 8, from part A up to part C. Oh, these are your questions, all of them. By the way, God rested on the 7th day. I think this is number 7. I better also rest here. Oh, there is still more. Still more of your exercise. I've given you numbers from basically number 5. Yes, up to number 8. Number 7 is there. You can write it down. And then number 8. Number 8 is still part of your exercise. You do it. Okay. Thank you for listening and thank you for watching. May God bless you. Bye bye. A nice time.